Hi, I'm Carl, and in this video we're going to go over questions 83 to 86 of the third section of the green paper. So this question is about chirality and about Fisher projections and isomers. Question 83 starts off by giving us 4 different compounds and asks which ones have chiral carbons. So a chiral carbon is a carbon that has 4 different groups attached to it. So let's go through and see if there's any that have 4 different groups attached to it, and I'll mark them in red here. So if we were looking at this one, this would be our best candidate. With these rings, it can be a little bit difficult to see which ones have chiral carbons. So this carbon here has a methyl group and a hydroxyl group and 2 carbons attached on either side of it. Because it's a ring, you need to go around the ring to see if the carbon atoms on either side are identical or if they're different. So in this case, if you keep going around the ring, it'll be the same on both sides as you keep going around. Until the lines sort of overlap, and so we can say that there's not going to be any chiral carbon here because they're identical on both sides. So this isn't chiral. If we look at this carbon, we can see that there's going to be a hydrogen that wouldn't be drawn in this skeletal formula. So we've 1 hydrogen, 1 methyl group, and then if we start going around the ring, we can see that this carbon that is bonded to and this carbon that is bonded to are different. So it's got 4 different groups attached to it, so it will be chiral. Again, if we look at this one, in structure 3, we can see that there's going to be the hydrogen that will be implied, the methyl group, and if we start going around the ring, we can see that this carbon and this carbon are different, and so it's got 4 different groups attached to it, and so it's also chiral. And again, if we look at this one, it's got a methyl group and this hydrogen that wouldn't be drawn, and if we start going around the ring, we see the first carbons are identical, but if you go around the ring for the second one, you can see that the chains are different, and so there's 2 different groups there, and meaning this carbon has 4 different groups altogether, meaning it's chiral. So that gives us an answer for 2, 3, and 4 only, meaning the answer to this question is going to be C. If we look at 84, then it says which one of the following correctly lists the groups of atoms in order of decreasing priority, which is going to be in order of atomic number, pretty much. Now, if you know the atomic numbers off the top of your head, this will help, but straight away, you might have noticed that oxygen is a higher atomic number than carbon, and so B would be the answer for this. But if you want to check the other ones, you just need to look at the atomic numbers of what the first atom is, and then if it's bonded to something else, there's a rule here that says if 2 or more atoms bonded to the chiral carbon are identical, priority is determined by referring to the next atom in each of the groups. So you have to look at the next atom in each of the groups, be it a hydrogen or a bromine or another carbon atom. And we can see that they're not in order for decreasing priority for the other ones. If we looked at C, for example, bromine has a higher atomic number than carbon, and so it wouldn't be correct. D wouldn't be correct because nitrogen has a higher atomic number than carbon. And then if we were to look at A, the carbon is attached to a hydrogen, and the other one on the right hand side, which is said to have a lesser priority, is only attached to another carbon, which would obviously have a higher atomic number than the hydrogen in the previous one. So B is the only one that's listed in order of decreasing priority. Okay, so 85 then is which of the following statements is true about the Fisher projections compounds 1 and 2 shown below. So I've drawn out compound 1, and I'm going to try and turn it into compound 2, and this will tell us whether or not it's superimposable, whether it's a mirror, if they're not related, and it will give us an idea of how these 2 structures may or may not be similar. But we can straight away rule out D and say that each have more than 1 chiral carbon. There's only 1 carbon atom there, which is attached to different groups, and you can see actually that each carbon atom is attached to more than 1 hydrogen, so the idea of chirality there wouldn't be true. If the center of this Fisher projection had a carbon in it, then of course it would be chiral because it's got these 4 different groups attached, but none of the other carbon atoms have 4 different groups because they all have more than 1 hydrogen. So we can rule out D straight away. And I think the best way to see what the difference is between compound 1 and compound 2 is to try and turn compound 1 into compound 2. So we've got this Fisher projection here, and I think the best thing to do straight away would be to rotate it. If we were to swap some of the grips around, there's some rules at Fisher projections, but if you swap some of the grips around, you'd have to do the same thing on both sides. So if you were to swap all of these grips around, what sort of changes would you be able to make? So, for example, if I swap this grip with this grip, we'd have to do the same thing along this sort of line of symmetry here, and swap this grip with this grip. And if we did this, we would end up with an OH grip here, a CH3 grip down here, a hydrogen here, and this ethyl group up here, which is compound 2, which means they are superimposable upon each other. I mean, the answer for this one is going to be A. And we just need to remember that there is this line of symmetry. If you're going to do something to one side, find the line of symmetry and do it to the other side too. It's okay to do that. That's how Fisher projections tend to work. Okay, so finally with 86 it says consider the Fisher projections of the following 3 compounds, which I've drawn out here. And we're going to focus on number 1 first, because it says that if we're going to look at an S or an R configuration, and this is information at the bottom of page 70, it says the molecule is observed from opposite the atom or the group with the lowest priority, which means we need to make sure that the hydrogen, which is the group here with the lowest priority, is opposite us. So another way of thinking of that is it's going to be at the top of the diagram. So if we had our line of symmetry here and we swap these groups, then it means we could swap these groups around. So what would it look like if we did that? It would put the hydrogen at the top, which is what we want. We'd have our carboxyl group here, our methyl group, and our bromide group here. So this is our lowest priority, this is our highest priority, this is our second highest priority, this is our third, and then our fourth. So if we were to go around, we would say if we go 1, 2, 3, 4, that would go anti-clockwise, whereas if we tried to go the other way around, we'd have to go around more than once. And so the simplest path to go around 1, 2, 3, 4 like this would be this anti-clockwise path, which means that it's going to be an S configuration. If the simplest way of going around it was the other way, then it would be R for clockwise, but in this case we're looking at anti-clockwise, so it's going to be S configuration. Now we've got figure 2 here, and we've got our lowest priority group at the bottom, which is fine, and if we were to label these as being low to high group, we can see that again it would be this sort of anti-clockwise motion that you'd have to do. And so again, sorry, the anti-clockwise motion, there we go, that would show that it's going to be an S configuration. And then what about number 3? Well, number 3 is that we've got our lowest priority group at the top already, and if we were to go through and label all the priorities, we would see that we'd have to go around in a clockwise motion like this, which means this is going to be an R configuration instead of an S, meaning that the answer for this one is the S configuration is only found in 1 and 2. The tricky thing I think about this question is this first step, labeling the groups and working what direction to go is easy enough, but it's knowing that you can make this change with the line of symmetry in those Fisher projections. I think that's the biggest thing to learn from this. The answer for this one is going to be D, because only 1 and 2 have this S configuration. Okay, so that was questions 83 to 86 of the green paper. I hope that helped.